So let's talk about this idea of accumulation. When we talk about an integral of any time if we get a rate, an integral of a rate is an accumulation of a quantity, okay? So when we take the integral of velocity, we end up backwards at position. But we're not always considering an initial condition. So I want to go through some AP style problems. This whole entire packet has to do with applications of integration. So what are things you guys can do with integration? So we've got water being pumped out of a holding tank at this rate. Okay, rate is in liters per minute, where T is in minutes since the pump is started. We have an initial condition of 300 liters of water when the pump is started. How much water does it hold 20 minutes later? Well, that's a pretty easy setup. This is a very classic integral question that you could see on an FRQ. So the integral from 0 to 20 of my rate 4 minus 4e to the negative 0.12 t dt should be equal to whatever water is at 20 minus water at 0. This is a first FTC reference. So when I take an integral of a rate, I should get my amount at 20 minus my amount at 0. Well, they did give me the amount at 0. At time 0, it's got 300 liters of water. So in essence, I can add this to the other side and say 300 plus the integral from 0 to 20 of 4 minus 4e to the negative 0.12 t dt, and that should give me the amount of water that there is in this tank at 20. Now, you guys can type this in your calculator and come to the conclusion that W of 20 is 250.309 liters. Now, a question like this, you guys have done a question like this before, a simple manipulation of first FTC. The kind of question you haven't done, though, is one like question number 2 and 3. It says, a city is located along a straight highway. The way that I would imagine this is, imagine if you had one road and the town square was right here, smack dab in the middle of this road, okay? So it says its density can be approximated by this function. Now, you need to know just in general, when we talk about a density is people per mile. Now, even though we're not talking about increasing this town, I want you to kind of think about density as a rate. It is a rate. When we talk about people per mile, it is the amount of people that are concentrated within a certain area. Even though we're not talking about the town growing or getting smaller, it is still a rate, okay? Because I have something per something. Now it tells me that x is going to be a distance from town square, measured from -4 to 4. So we've got some distance, -4 on this side and +4 on this side. And x is some distance on either side, okay? Now it says the town extends for 4 miles on either side of the town square. Find the population of the city. If I take the integral of people per mile, I should end up with people, okay? Because dx, when we talk about dx is really with respect to miles. So what we're going to do is we're going to take the integral from -4 to 4 of the rate 1500 times 4 minus x dx, throw it in our calculator, should get about 48,000 people. So the big takeaway from this problem is that the integral of a density is a population. The integral of density is a population, okay? So we can extend our thinking just a little bit more and say, hey, it doesn't make sense for a town to really be along one road, okay? Typically, when we talk about densities of people, we're talking about in a circular radius of a city. So it says a city can be approximated by a circle of radius 8 miles. Moving away from the center of the city, the population density can be approximated by this function in people per square mile. Write an expression to represent the number of people in the shaded ring. So we know that density is equal to population per some area. If I solve this, I can say that population is equal to density times area. So I want to find the area of the shaded ring. And the shaded ring is all of this stuff. Okay? So if I want to find area of a shaded region, I'm going to need to multiply by the circumference. Circumference is 2 pi r. And its thickness is delta r. And you can see that right here. Now, if this is the area of the shaded region, okay, I'm going to now find a way to represent people. People should be 2,000 e to the negative 0.15 r. That's my density. And we're going to multiply it by the area, which we said was 2 pi r delta r. So I'm literally saying in this expression, density, and this is the area of the ring, okay? Now, when I want to apply this to find the actual population, we need to have from where to where. Well, we're going to go from 0 to 8 because it was an 8-mile radius of the 2,000 e to the negative 0.15 r times 2 pi r dr. And you can plug that in your calculator and really quickly find that you get 188,424 people. So why is there this extra 2 pi r? Because we're dealing with a region that is circular, okay? And this idea that it's density times area, okay? So really what I'm just modeling for you is the kind of questions that you could see that are very, very AP style. I want to walk through one last question, kind of start to finish, which is an interesting question. This actually popped up on the 2005 AB test. This was the calculator question. So this is a calculator active question. And this is very much like an accumulation AP style question you could see. So we got a beach, and basically we've got tide removing sand. So this is sand going away, and this function is a rate. So that is the rate of removal, okay? Now, because we're removing sand because of erosion, we want to add more sand to the beach. So this is the sand being added to the beach. And again, it is also a rate. Okay, so the first question says, how much sand will the tide remove from the, that should say beach, during this 6-hour period? And if we're talking about removal, I'm talking about r of t. So the integral from 0 to 6 of r of t dt, integral from 0 to 6 of 2 plus 5 sine of 4 pi t over 25. Don't forget a dt. And when I throw that on my calculator, I end up with about 31.816 yards cubed, okay? And I know that because it says we're talking about a unit of cubic yards. So in 6 hours, that is the amount of sand that is going away from the beach, okay? It now asks me to write an expression, y of t, and if they tell you y of t, you have to use that letter, for the total number of cubic yards on the beach at any time. Now, We need to do this from a logical standpoint. If I have a function y of t, it should be some initial amount of sand, what is there to start with, plus the sand that I'm gaining minus the sand that is being washed away, okay? So y of t, it tells me in the problem there's 2,500 cubic yards to start with. Gained, we're talking about the sand that is gained, so that's an integral. I'm not just talking about the rate of sand, I want the sand that is gained. So my equation for the sand that is being added is 15t 1 plus 3t dt. And actually, we're going to change all of these t's to x's. And I'll explain why. Because we're going to put our t up here as the bound. Okay? Because our bound is saying, hey, from 0 to some time t, which we don't know, I'm going to be adding sand. And then our sand that we're losing is going to again be an integral, because it has to be the integral of that rate of 2 plus 5 sine of 4 pi using x over 25 dx. And this integral is going to go from 0 to t also. So this is my expression for y of t. Initial amount, when I take the integral of the rate of going in, that's going to give me my sand that I've gained. And when I take the integral of my rate that is being washed away, I should get the amount of sand that is washed away. It then says find the rate at which the total amount of sand on the beach is changing at time 4. Well, I want a rate. If this right here is our total sand, then a rate of total sand should be the derivative. So we're going to take a derivative piece by piece. When I take the derivative of 2,500, I get 0. When I take the derivative of this by second FTC, this should just end up being S of t. And when I take the derivative of this, it's just going to be my function R of t. And so if I want to find y prime of 4, it's going to be S of 4 minus R of 4. So you're going to go up to the top of the page and you're going to plug 4 into both of those functions. When you do that and you plug 4 into both of those functions, you should get about negative 1.909. I need a unit, yards cubed per hour, because this is a rate. Okay? Now for the very last one, this is where I'm going to kind of turn you loose. It says from 0 to 6, at what time t is the amount of sand on the beach at a minimum? That is an absolute minimum. And you need to know that anytime I want an absolute minimum, that is candidate's test. So step 1 is that you're going to take your rate and you set it equal to 0. So basically, S of t minus R of t from up here is equal to 0, which is basically saying S of t equals R of t. Well, if I go to my calculator and I plug this in y1 and I plug this in y2 and I use my calculator, you're going to get an intersection, okay? I'm not going to give you that intersection. You're then going to go and candidate's test. You're going to have your endpoint of 0, because it says 0 to 6, your endpoint of 6, and whatever this number is going to go right here. And because I want to find the minimum y of t, you're plugging this into y of t. So be careful. Y of t is that guy. So you need to plug in 0, you need to plug in 6, and you need to plug in that point and tell me which one is the minimum. And I will check for this.